Good morning, everyone. Can hear me, right? Okay, so this will be the last tutorial as we are into week 14 now. But there will be a lecture tomorrow morning, right? So it's still on. Now, before sorry, before we jump into the this tutorial, any questions from the previous tutorial on swarm intelligence or anything else on these maybe recurrent neural networks? No? Okay, everything is good. So let us go into the tutorial. Any questions so far on the, if you've seen the tutorial, any questions that we want to ask, right? Nothing. Let me set up look at the chat box, just in case you have any questions to ask. Okay. Now, let's look at the first question. Now, you have to design, right? Design a discrete Hopfield net. Remember, there are two types of Hopfield nets. Where you see, one of them is the what do you call it? The discrete. Basically, you work with either 0, 1, -1, and 1, right? So it's discrete, binary, if you like. The other one is your what do you call it? The continuous. I just wondering where is my microphone? Microphone. Okay, microphone cover. No, it's gone. So the sound today might be a bit off. Looks like the microphone has something one pass missing. Oh, so back here. Sorry, back here. So can look at here. Maybe I can increase the size. All right. So you have to design such a discrete Hopfield net to store these two particular input patterns, which is, let's call this pattern A, and let's call this pattern B. Now, this one may not be so obvious it is basically a pattern. But if I were to draw this out, so you might hear some wind noise because the microphone, the cover came off. It's sensitive. Right? So you have this. You have this, which is basically a I call it the three pixels, if you like, right? So let's say we have -1 is black or darkened, shaded. So for can see pattern B now is very different because you have this kind of pattern. Now, so you have to design such a what I call the discrete Hopfield net to learn this particular two patterns. Now, what can you tell me about the characteristics of this Hopfield net, especially for this particular application, which is remember what is this? This is application is what do you call this? Associative memory. Excuse me. Let me have a drink of water. Okay. So for this particular application, which is basically an associative memory, supposed to recall by association. I see something, I can connect back to that fragment of information for the rest of the information. That is basically another, what you call that, the layman's explanation, layman uh, definition of, or description of your associative memory. So for this particular application, how many neurons do you think I need? And then what are the characteristics of such a object? That Chongyi, maybe let's start with you first, if you're ready. If not, it's okay. Yan Chang, maybe, or someone else. Sorry, yeah. Anyone? Anyone? Last week, oh, you don't want to speak up. Well, okay, never mind. I think you guys are maybe still still haven't woken up yet. So basically, okay, this part. Okay. Never mind. So okay, it's my job to make sure you understand. So basically, if you can recall, recall back, think back in the lectures, you have several types of neural networks. We have talked about the feed-forward types, right? The feed-forward type, which is the multi-layer perceptron. Now, what is the difference, if you like, between this and this particular recurrent neural networks? So, if you remember, the Hopfield is a, uh, should I say, member, part of, is the family of, in the family called recurrent neural networks. What does the word recurrent means to you? Anyone? Let me see. Anyone responding? No. Because my greatest concern is if I continue with this as a lecture, so it's no different from the previous day's lecture. But tutorial is not meant to be lecture. It's supposed for you to participate, so that it will complement, right? It will complement the learning process. That's why I need you to participate. Anyone? Maybe if not, I'll have to pull up some of you. Let me see. Kashing, Kashing, just tell me what is the characteristic. If you cannot tell me how many neurons do I need, which is part A, you see that, part A. How many neurons do I need? If you cannot answer that, okay, good. Kashing, well done. So it's actually 3 neurons. Can see, obviously it's 3, because later on you find that I think in the other 4 other groups, some told me 3 by 3, some told me 3 by 2, right? Of course, some also tell me it is 3 neurons. So Kashing is correct. It's 3 neurons. Now, after that, 3 neurons. What else can I? What is the main characteristic of such a Hopfield net? Other than the fact that it's now we're using binary or discrete. Let's see. Heng Dong, Mr. Hu, can you tell me anything about the characteristics of the this particular 3 neuron Hopfield net before I show you the how you calculate? Heng Dong, no. This morning also I see very few of you. Only 9 of you, I believe. So I think you're starting your holidays already. Hang Xiang, how about you? Anything about the characteristics? One of the major characteristics of your uh, Hopfield net. Okay, give you a hint. Okay, never mind. Hang Xiang, so basically I've not done a good job. So basically, it talks about the feedback, right? Does it have feedback? Right? So this is a recurrent neural net. So as I said before, your recurrent is actually different from your feed forward because it has feedbacks. And what else can you tell me about the feedbacks for this Hopfield net? So few of you. I've got Hang Xiang, I've got Heng Dong, Hang Kashing have replied. Leong Ho, how about you? What can you tell me about the feedbacks for this particular recurrent neural net? Mr. Teo, knock knock, are you there? No one knows. Maylin, now you're the next one. Sorry, so few of you. So your turn will become quite frequent. What what is the characteristic of your basically your this particular something to do with the feedback? Ayo, you fellas don't know. Your exam is on the 6th, isn't it? Not that far away, right? Okay. Hang Xiang, you are close but not correct. It has there is no self feedback. Maybe you're saying that. So it talks about the feedback for this particular Hotfield net. One of the major characteristics is that it doesn't have any self feedbacks. Okay, let me jump back to the figure. Okay, now I have this. So I want to draw this out and shrink a bit. So now okay. This line, your line today is not very stable. Looks like it. Looks like yesterday. I think some of for those of you they joined me in the web seminar or webinar with analog devices. I'm surprised. I've been working from the campus for about 1 year plus since the what they call it the pandemic started, and then I never had problems with the network. Yesterday, for some reason, the network crashed for about half an hour, so the line was down right in the middle of our web seminar. So maybe it's a way of saying that the whole situation is becoming back to normal in the sense the network will also crash. I thought if I work from home, the network will not be stable. So just to make sure the network is more reliable, I actually work from the campus. But even then, the network actually crashed. And then on the other hand, my personal network was more stable. So okay, so we have feedbacks, which is Hang Xiang is correct. But then in this case, the what I call the there are no self feedbacks. So my hand today can see my hand not very steady today. Sorry, Oops, sorry. Oops, this is no good. Oh, okay. I cannot. I gotta erase it this way. Let's try again. Maybe let's make it smaller, easier to draw. So I'm gonna go all the way so you can see. Basically, I'm trying to build the what I call it the feedbacks. So of course, while I'm drawing this, you can also ask me questions. So if you do not understand, right? Well, maybe some of you say, "Oh, it's still too early." Okay. So let's do this. So this is my connection. Oh, sorry. I think I know why. I was using this. Satu, connected, connected, connected. Right? So again, in the exams, if such thing come up, when you draw, you pay attention to such things. Make sure it's you have this. Make sure it's to show that it's connected. Then you have this now. So this is, let's call this neuron 1, neuron 2, and neuron 3, or connect output 3. Right. So in this case, you can see that here I got this connection, and then no self connection. So this is connected. This is connected. And number 2 here, you trace this one, right? So this is connected, connected, and then the last one with this one. Just to show you, this is not connected. Maybe I'll do it the other way, show a different color to highlight to you this is not connected. This is not connected, and this is not connected. Is it clear? Maybe it's too small, is it? Let me see. Can see it not? Okay. So, Ang Xiang, so this is no self connection. That's one of the that's how it works anyway. That's how it was designed to work. So now, next thing is what else? So now we have to. So we have answered the part A. Now we have to answer the other part, which is um, how do you show that whether the two patterns here, A and B, are they stable? Right? There was the question there. Are they stable? So we this one answer is. So the answer is 3, right? So are these stable memories? Right. So what do you mean by stable? Right. So basically, if you remember, what it means is that if you present back the same pattern, does it converge back to the same input pattern, right? Or does it go to a different pattern? It's still stable, or does it oscillate? Right? You might see all that. So you have to show all your calculations to show that this is stable or this is not stable, whatever it is. So what do you need to know? Right? First of all, of course, you need to figure out. First of all, how to figure out the very important thing for such neural networks, which is actually we have to calculate the weights, which is shown here. Okay, so to help you to calculate the weights between I and j will be summation. So it's called the input I, input j, input I, what do you call it? Input I for pattern A, S. So in our case here, the pattern there are two patterns A and B. So there will be um, let me see 1 minus 1 1. Okay, so let's again do this. Let's see if we a different color. So A, oops, sorry. So I working with a digital pad is still not the same as the sensitivity. But then again, like you said, engineers or inventors or engineers, as long as you see that if there's a problem, it's an opportunity for you to do better. 1 minus 1 and 1. All right. Oops, sorry. Cannot. Now B will be minus 1, 1 and minus 1. Right? 1 minus 1. Okay. So I have 3 neurons. Sorry. Mm. I have 3 neurons. So I should have back to my hang on. I think this is very distracting. Give me a minute. Yeah, Zhou Yi, sorry, because I went out because there was the dog was I think there's a cat in front of the gate, and the dog is making a lot of noise. So sorry about that. So now I put the dog somewhere else so that it won't be distracting. Sorry about that. So yes, so back to this. Now where am I? Okay, now we have to figure out the weights for this, right? So this is 0. So we have three what do you call it? Three neurons. right? And two patterns A and B. So let's see now, we have this. So I want to calculate the W, the weights. So I have, let's say I have this. I have one, I have two, I have three. So this represents a tree. So let's look at the connection between 1 and 1. Let's go back to Hang Xiang. 1 and 1 here. So this one, I'm looking at this, right? 1 and 1. So 1 connected to 1. What is the weight over here? Hang Xiang, what do you think? Chung Yi, want to help? Or anyone else? Anyone? No. No one. Right? Because as I said, since there are so no self-feedbacks, how to represent no self-feedbacks? So you put a croissant. So you can see here, no self-feedbacks. Right? Now, so then we have 1 connected to 2, this one over here. Or is it 1 is to 2? 1 is to 2. 1, oh, sorry, 1 is to 2, this one. Right? 1 is to 2, right? So what is the weight for that? Let me see. Got to invite some of you here. I know some of you just came in. Okay. Yan Chang, how about you? Want to try? The 1 is to 2, the second column, first row. What would be the weight? Okay. So you look at the equation here, right? Given here. So what do I have? Okay. So I have here, maybe I look at here. So it's actually, I'm looking at this one, this pair. 1 is to 2. Right? So I have 1 for the first pattern A, right? S equals to 1. So first minus 1. Then sum up the second pattern now, which is the same place, the same pair rather, right? So minus 1 and 1. What do I get? You get a minus 2. Is it clear? Okay, now I want you to try. Siapa lagi? Hang Xiang, want to try? So that we can quickly finish this. Otherwise, I'll be late again to finish up after 9 o'clock. Yeah, 2. So this is 2. So to be consistent, put a plus 2 there. 1, 1. Okay, correct. Let me just erase this. So that's the first step. First step, you have to calculate the weights. After you have figure out what does your network looks like, the architecture, right? So this is right. So it's 2. Now I share with you a secret, a secret. Shh, secret. Don't tell people. Sorry, I know it's a very lame joke. Now, does it matter if it's back here? Does it matter which comes first? Does it matter if I say 1, 2, right? And then or 2, 1? Doesn't matter, right? It's not. It doesn't depend on which one you select first for your calculation. So what I'm trying to say is that so here 1, 2, and 2, 1 will be the same. See that? Because this basically it means that this is a you only need to do half the work because you can copy down here. So this is what do you call, what's the word? They have a equal diagonal because so top half of the matrix is the same as the other half. It's a diagonal matrix in a way, right? So we only need to calculate the last 2 here. So this is 2, 3, right? 2, 3. Now who wants to try 2, 3? uh, Yan Chang, want to try? Sorry, is it Yan Chang just now? Or is it Ang Xiong just now? Yan Chang, want to try? The 2, 3, the weights for 2, 3. This one here. 2, let's see. 2, 3, 2, 3. Okay, sorry, my screen is small. So I thought it's plus, so it's correct. -2 and -2. So the step number 2, you calculate the weights. This is step 2, right? This is step 1. You have to draw out there, show the basically the architecture or the system. So now done. So that's the number 3 now. Step number 3. Now we try to calculate, see, test it out to test pattern A and then pattern B to show or to show to ourselves that it is indeed stable, it is indeed unstable or whatever, right? So first one is A is 1 minus 1, 1. So let's try A. 1 minus 1 and 1. Now, I think I can't remember whether the equation is given. So your new output, let's call it Q, will be I think this is I, this is J, this is N. What else? This is yes, the what do you call it? This, let's call this X, J. I hope I got this correct. Right. So this was basically at T plus 1. This is actually T. So now you can see it is now dependent on the now. So this one will be the new outputs based on the previous inputs. Boleh faham, right? So now with this equation, right? So let's look at the first one. Equals to 0 minus 2, 2. Let's draw this out. I am doing this 0 minus 2 and 2. This is plus, plus. I have another bracket here, which is my input. Okay. Now what else? Okay, now I fill in the inputs, which is A. Okay, so what I get? This is 0, this is a 2, and this is a 2. Yep. Good. Yang Sang, thank you for participating. Got a 4. Now, what is the other part that I have not discussed so far? Let me find some space. Oops, sorry, no space. Maybe I'll do it here. So if you remember, the neuron looks like something like this, right? Our basic, our good friend, the perceptron. So this is the summation part, and this is your non-linear part, right? So non-linear part. So basically, it is the what's the other word? Transform. If I may say so, you might use the word transform, right? So for the transform, what do we use? We use this. I think the other thing we have just finished was under the support vector machines is the kernels. So what do we use? Do we use a sigmoid? We use the hard limiter. We use the Gaussian. Blah blah blah. What do you think? So now, if you use something that, of course, you have to go back and look at your patterns itself. So it's only 1 and -1. Are there any zeros here? No. So basically, what does it mean? It means that we have to use a sine function, which is f of x equals to either a +1 or a -1. So now, if we say that is only if and only if x is more than 0, otherwise. What does otherwise means? It means that if x is less than equals to 0, be careful with the equals to 0. You can also do this. You can also do this and show it clearly. I can do this, right? X is more than 0, I get a +1. If x equals to 0, I get a -1. And x is less than 0, I get a, maybe if I do it this way, this is, I think maybe a better way to show this. Okay, now question that was in the other class. Why do I choose 1 and -1? Anyone? Why do I choose 1 and -1? Why not? Why do I choose? Why not -1 and 0 or +1 and 0? Anyone? Kasing, good try. No, it's not. It's not the classes as I said. You go back because you see here. Let me go back here. No, let's say we choose this. We choose this. Maybe I'll choose a different color. Right. So now let's say we choose f of x equals to let's say +1 and 0. Right. So let's say that we erase this. This is our step 3. We're trying to calculate the step 3. Right. Let's say this is true. So x is more than 0. X is less than equals or equals to 0 is a 0. Right. So now, Zhongyi, no, it's not direction. Look at this here. Now, what does the nonlinear function does? What does it do? It does something like this, right? So any value, it is your input. This is your output. Now, if your input is here in this 4 over here, you get a 1. Now, what about if the input is here, right? See that? Less than equals to, so somewhere here. So if you put 0, let's say this is -4, let's say, so what's the output here? Zhongyi, what do you think? What's the output over here? If it's -4 in this example, what's my value here? Right? If I use this particular sine function. Kasing, what do you think? Anyone else? To help out so that I can move on. Right? So you can see here, if it's x equals to -4 now. Right? So what is -4? What's my output using this function? Anyone? Maylin? Right? This is my non-linear function. So x is -4 now. So what's my output if I want to transform this using this particular function here? What's my output? Maylin, are you there? Or am I confusing you guys? Right? So let's focus on this. F the function to transform this particular value here. So it can be either +1 or 0. So when do I get +1? When x is more than 0, or when x is less than 0, or less than equals to 0, I get a 0. So if my x is -4 now, what's my output after going through this transform, which is if you represent it graphically, it looks like this. So it's -4 over here, -4. So what's my output? This is actually not 0, this output, in case I confuse you. Million? No. Let's see who else. Correct. Sorry, my thing stuck. sorry, my fault. Right? So you can see here, right? So it's 0. Now, if this is 0, what happens? So you can see that A is here, A0 is here, A1 is what? Then becomes a 0 over here. Now look at it. Does it make sense that at the end you get something like this? So what do you think? Right? Logically, it doesn't make sense because it cannot be 0 because look at the outputs here. The actual patterns here is only either 1 or -1. It cannot be 0 and 1. So therefore, yeah, I have to take this. I have to take this. Right? So is it clear now why we have chosen the transform the transform to be +1 and -1, right? Can I move on? Right. So if it's right, so this is basically what it is. So that's why we have to, and the same applies. So this one actually is a function of your application and your input patterns. Okay. So it's function of that. Let me just erase the rest of this. Chung-Yi, is it clear? Clear? Hopefully it's clear enough. Any questions, comments? I just erase this. At least you clear the clutter. So basically, I think if I may recall yesterday's web seminar given by your senior, many years of senior. So I think he's actually smart in the sense that after he actually graduated, he finds that if you want to be successful in the industry, you have to be able to communicate clearly what you're trying to say. Either way, or you can also ask questions. So again, so again, as I said, you're now in the university. You're supposed to be training to be successful later in your career, right? So again, I also encourage you, although it's a week 14 now, encourage you to actually ask to communicate, ask questions, especially if you feel that you are not so good at talking. So of course, that's why I think Desmond Ooi yesterday, he actually got himself signed up for this Toastmasters club, which is public speaking. Train so train you to become a better public speaker. So back to here. So now it's 4. What do I get? I get a 1, right? So now at t equals to at a1, the next time step, I get what? I get a 1 here. Okay. Then I can also do the next one. So next one, I change the weights. So what do I have here? The second one is what? Second one is -2, kosong -2. Okay. So what I get? I get a -2 here and a -2 over there. -4. Now, -4. Now, you see a -4 here. So imagine if you have used a 1 and 0, right? So you get a 0 here. So this is actually all out, so that forever your network will never be produced back the same results, right? That's why we have wisely chosen 1 and -1. So you get a, what's the value here? Let me see who else can I invite. Shuwen. Bang Shuwen, what's the final output for this? Bang Shuwen, are you there? or can someone help him? Yep, -1. Thank you. Yang Shang and Ka Xing, thank you for that. So I can move along. So you get a -1 because of the, you put this inside your this sign function. So because it's known as a sign function because actually it is a, you look at the sign. Of course, 0 is a special case. 0 has no sign. So you just assign it to either one of them. So notice here, I've just, no one asked me. I don't know, maybe you all did see this. I've just selected this to be in -0 as -1. I can also assign this to be a +1. So of course, the results may be slightly different. It will shift a bit in terms of the results. Okay, so we get -1. So now I have a -1 here. So I will erase this. Okay. And the last one, 2 minus 2, 0. 2 minus 2, kosong over here. Right, so what I get? I get a 2 here, I get a 2 here, I get a 4. Right? So I think I better speed up. If I don't speed up, I will never finish it. Right? So what I get? I get a +1. Right? So I get a 1. So A2. So I'll calculate. Now when t equals to 2, I calculated t equals to 1. Now I want to calculate t equals to 2. Okay. Question. Is that necessary? Ding dong. What do you think? Is that necessary? Or rest of the class? Do I need to calculate t equals to 2, t equals to 3, t equals to 4? Answer is no, isn't it? Because it's obvious, because you can see actually if I calculate 1 million times, it will be still stable. It will be still the same, right? So you don't need to calculate unless you are not sure. Right? You see that the pattern is different. So this is basically, I think, as you know, this is actually the system has converged, right? Has converged to that stable state. So the condition is, the answer is yes. This is a, so first one is stable, right? So A is stable, for A, right? So we've done that, right? Now for B, I want you to go and try on your own because I don't want to, I don't have the time to calculate for B. So it'll be the same way. Can you do that? Yeah, can you do that? So so I can skip and go to part C now. Now part C, you're now asked to test the Hopfield net. This Hopfield net that we have built with these following uh, two test patterns. Obviously, these two are new, right? So if I would show it to you, this is right, and this is what, so you can see. Let's call this now pattern C and call this pattern D. Right? So now, what can you say about these two patterns? Again, even though the question seems very innocent, simple, you have to calculate, do some calculation to show, to analyze, to see what is it doing, right? Or what can it do? So it's -1 and 1. So if I can just erase this, do it this way faster. Again, please, I need to keep reminding you guys, if anything you're not sure, please ask. Okay, so now I have this, this. Oh, I think, sorry, this is, I think, correct. Only this one is different, right? This is my, oh, sorry. Sleeping, I think. This is pattern C. Right, so now pattern C. Right, -1, -1, -1, and 1, -1, -1, and 1. So pattern C. Now, what do you think will happen? So now I have to do this. Okay, so the first line is same thing. 2 minus 2 and 2, isn't it? Go back to the same weights here. Now, there was a question again last week or in the other classes. Do I need to change the weights? Do I need to change the weights? Because now I'm now testing it on pattern C, which is very different from the pattern A and B. What do you think? Who wants to try? Wen, are you there? So this is a simple binary answer, yes, no. Wen, I think not here, I think. Probably not here, is it? Don't know. Okay, I don't know what that question mark means. Question is, do I have to change the weight that we have calculated here? Because now I'm now trying to calculate trying to analyze pattern C, which is very different from the two patterns that we have done before. So these weights here are based on A and B, right? So when I want to test it against C, do I need to change the weights over here? We go back to the question here. Test the Hopfinet, right, against the test patterns, which is C and D. So now, can I just calculate based on the same weight, or do I have to change this weight as well? Because as I said, no, this was based on this. Xuan, what do you think? Yes? Not sure. What the rest of you think? Let me try another one, another person. Yep, Hang Xiang, thank you. Right? No. In a way, I would say I'm trying to confuse you, right? Because yes, the weights here are based on these two patterns, but then again, let me see. Let me see what Carson is asking. Let me see. Hang on. So A and B is to train the weights, then C and D is to correct. So it's like saying, I give you I give you this. You try it on this particular question, right? This is a tutorial. Now in the exam, I ask you to design a pattern which is a 4 neurons. So now, maybe not a good example. Let me try another one. Erase that. Try another one. We have seen what apples and oranges look like, right? You know the apples are green and red, right? And oranges are orange in color. So you have actually, your brain has formed the weights to recognize apples and oranges. Now tomorrow I give you a new pattern which is apples, which is yellow in color. Do I need to retrain everything, or will you straight away tell me that, hey, this is an apple? Does that make sense? That analogy, that example, does it make sense? Right? So this is the same concept. We have trained the network A and B. Now I'm giving you a pattern which is called C. Right? So again, same thing. Another example will be, you've seen your friend. Let's say Yan Chang has seen what Zhongyi looks like. But so in Yan Chang's brain, the weights will have formed to say that this one, as long as I see Zhongyi, I know this is Zhongyi. But next day, Zhongyi decided to either wear glasses or he has not cut his hair for past 6 months because of the MCO. So his hair is very long now. But the new Zhongyi with a long hair is actually still looks a bit like Zhongyi, isn't it? Right. So therefore, I don't need to retrain. But if I were to say I want to look at Leong Ho, for example, right, and Yang Chang has not seen Leong Ho before, then maybe I need to retrain my network to actually include that this is Leong Ho, right? Does that make sense? Right. So back here. So now let's try this. So now we have this. So now we have this here. I need to speed up a bit. I think we're running out of time. So now we have this. So we have this kosong. This is a 2 and a 2. So this is a 4 and I get a 1, right? So I get a 1 here. Notice this is C T plus 1, T1. Now, quickly, we do this. We change the weights on the second one, the second pattern. This is -2 and -2. -2, kosong, -2. So I get a 2 and a -2. Now, this I get a kosong. What do I get? Right? So I got a, so since we say that this is a, if we take -1, sorry, 0 as a -1, so this will be -1, right? And last one, the final one. So this +2, plus and -2, 2 and -2. This is kosong, right? So what I get, -2, 2. Again, kosong. So we get a -1 again. Over here, see that? So -1. Now, so obviously you can see that I don't know what I think we cannot tell what happens after this, right? So after this, does it go back to this or does it go to A or whatever? So it doesn't matter. So we need to calculate again, right? So we need to change this. So this will be the pattern will be based on the previous one. So this is 1, -1, and a -1 here. So this is 2 and 2, isn't it? Got a 4. So I got a 4. I get a 4. I get a 1, right? So I get a, the next pattern will be over here, a 1. Now, if I were to erase this quickly, -2, -2. I'm going backwards, going back from bottom to top, so that to speed up the process. Don't waste the time. 2 and 2. Kosong again, you get a -1, right? So I get a -1 over here. And the last one will be this one will be -2 and 2, I think. I think it's -2 and a 2, remember correctly. Sorry, I'm going too fast for some of you, because I'm running out of time. So what I get a 2 here, and I get a -2, isn't it? Correct? Right, -2 and 2. So I get a 0 again. So I get a -1. Yeah, what do you see? So this one is actually Same as this, right? So if I were to able to draw this up for you, okay. So what do you have? I can see that I have my C0, then I get my new pattern C1, but this is actually not stable, right? It actually come back to this, right? So what does it mean? It means that basically my pattern actually is oscillating, right? So this is your, so my pattern C actually oscillates. It's not stable, right? Oscillates. It doesn't settle to a stable pattern. It flips between the actual C0 and the new pattern called C1. So for D, I'll leave you to, okay, now it's 9 o'clock. I'll leave you to try it out on your own, right? For pattern D. Now, the question D here, you are now asked to modify, right? So since you're asked to modify, you have to now change the weights. The weights have to change. Now it will be 3 patterns, right? So you have to change this to include A. Let's see here. Now this is minus. This is all one, isn't it? So basically it's a pattern D, right? Pattern D. So you have to train it to A, B, and D. Let's try for the first one here. Let's try this one here, right? So this will be um, 1 minus 1. So 1, 1, 2. Then this will be 1, 1, 1. So this will be minus 1 and 1. Plus the last one will be 1 and a 1, right? So D is a 1 and a 1. D here, isn't it? Here, modify this, include additional pattern, right? 1, 1, right? So what I get? I get the minus 1, minus 2, and then 1 together, minus 1. So this one will change to becomes a minus 1. The same applies to all this. You have to change all this. Okay, so that's your part D here, right? So the part E and F, you can get it from the answer will be from the lecture notes, the time attractors you have, and then what are the major problems of the discrete Hopfield-Net. Basically, it's a poor memory storage. You cannot store, you cannot remember too many things, right? Now, if I can quickly run through this, so this one shows you the this one answers are all given here, right? You can just try it out, right? So now no self-feedback. Now the other one is here, right? This one again, you basically have to use the equation to look at these pairs, right? And then the answers are given here, right? You have to now you have to use the you have to use the intercity distances over here as well in your calculations. You get this. The last one, the last question here is here. Now this one I want to I'm gonna spend some time a little bit quickly run through this. So let's say these are my I just highlight for you all the. This is actually converge. This is 10 city. So yes, network will be 10 by 10 neurons, right? So 10 by 10 neurons, you have this. Now, let's say that how do you interpret, how do you read this particular output pattern here so that it makes sense for you, because I'm trying to find the TSP over here, right? So what do I get? So let's say I start from here, A. So you look for the neighbor. Now, neighbor can be either left or right. This is left and this is right. So let's say we take the left neighbor. So from here, who's my left neighbor? F. So I know that A goes to F. And then you proceed the same way. After F, who's my neighbor? B. After B, who's my neighbor? E. Oh, now who's my neighbor to my left of E, of this first column? Right, as I said in the lecture, this is basically a toroidal space. That means this first column. Where's my pen? Okay, where's my pen? My pen is dead. Oops, sorry. Looks like my pen is dead. There you go. So this one, right, is toroidal. This will fold back to this side, right? So the first one will be neighbor to the last column here, column 10. So here, my neighbor will be H. H. After H, you get B, D, right? So question now is can I start, instead of taking the first row, can I start from anywhere here? I can, because this is a, so it's a circular, right? You can see that if I start from F here, I'll get the same answer. And the same also applies if you do not wish to take the left hand side. You can also take right hand side to you. But as long as you are consistent, if you take right, always take right. You don't take right one time and the next time you take left, right? So can also take, but for convenience, we take A. Start with row one, right? So this is answer. The last one here is, now this one is okay, valid, right? You can see, if remember, we said before, for a valid tour will be one row in one. Okay, maybe I'll use the other word. One satu, number satu in one row, and one satu in each column. So this one satisfies the two conditions. And of course, there are maximum of lima, in this case, lima said 1, 2, 3, 4, 5. 5 satus in the whole matrix. So again, this is valid. How about this? Here. I can see here. So this one, no. This row, no, right? We have 2 1 already. This column also no. So this is invalid tour. So here, if I use back the same here, right? How do I interpret my tour? So if this is A, sorry, this is A, B, C, D, E, right? This will be, let's start from B. I go from B to my neighbor will be C, then will be D, D to E, E to A, and then A back to B. This is my tour. This one I cannot, because since you have two of them here, right? I will get the wrong answer. How about the last one here? Before we wrap up for the day. Actually wrap up for the whole semester, except for the lecture tomorrow. So can we, is this correct? It's also valid, right? Right? So I think that's we stop here. Are there any urgent burning questions? Otherwise, you can go for your next class or to whatever you are supposed to do after this. So I'll leave you to try the first part, pattern B, and then the question one, the pattern D, and then the last one here as well, to also convince yourself. Now with this new pattern they have a design included into the modified Hopfield net, are the three patterns A, B, and D still stable? Are they stable? So answer the question by doing what we've done so far, which is actually calculate this. Okay, so we'll stop here. Are there any questions? If not, okay. If not, bye bye. I'll see you tomorrow morning. 9 to 12, right? We finished the last tutorial 9 on the, and then on the what do you call it, on the deep learning networks, and then I think after that we should have enough time to do a revision of all the topics we have sort of covered in the past 13 weeks. Okay. Okay. Bye bye. See you tomorrow. Yes. Thank you. Bye bye.